This is where we left off in class on Friday. I believe today will be the last new material I'm going to present for the semester. I have your grades up to date. Every single thing that's been turned in, I believe, is graded and recorded there. Keep in mind that we do have like the presentations tomorrow. That counts as equivalent to 4 labs, which makes it roughly equal to 8 to 9% of your overall grade. Right now, your grade is assuming that your score on that is going to be the same as on the rest of the labs. So your grade probably won't go up much from it, but it could go down if you tank it, just so people are aware of this. I don't expect people to tank it. I expect it to be good for everybody, but just want to make sure that's out there. There's a homework assignment that's due tonight. There will be another homework assignment that's due on Wednesday, and that will be the final homework assignment. Reading quizzes, there is the one that actually all but one of you have completed already that was originally inadvertently set to be due the Friday of the Nebraska Academy of Sciences that I moved to the last Friday of the semester. So that one person can still do it and get full credit for that one if they need it. Otherwise, I think we're pretty much there. So let's move on with class. Remember I said...
Oh, is that also kind of the scrapbook?
Oh, yes, there's the scrapbook as well. Right now, your grade is calculated assuming that you get the same grade on the final one as you had on the others. So the scrapbook being worth 10% and the final scrapbook being worth 1/5 of that, then it's about 2% there. Yes.
So you said earlier that the scrapbook, like we have to do 5 more
Yes,
submissions.
from anywhere this semester.
And then what chapter can we go up to?
You can go, well, I only lectured up through 31.
Okay.
But if you want to go to 32, you can.
Okay.
Right. At this point, if you find something interesting in physics that, we didn't get to, yeah, go ahead and use it. Mira first, then DJ.
Are you doing the extra credit with the scrapbooks again this semester?
Yes, I will.
Okay.
Yeah.
Can you please do what you did last year at the end and send out like some type of Google?
Oh, I've already done that.
Okay.
Yeah, I forgot to mention that. Yeah, if you look at the top of the class on Moodle, it has a spreadsheet for Windows and a spreadsheet for Mac. At least using my Windows computer and my Mac computer, they both work.
Oh,
so,
talking about something else.
Oh, no, okay. So there's a spreadsheet to tell you where you stand and what grade you need on the final if everything stays the way it is. Okay, so what was your question? I misunderstood that.
Yeah, so each of my 5 slides, they never actually fit into Moodle. And so if I'm going to send in the whole scrapbook for like the end, I remember last year you had like some type of thing we could upload it to where it would accommodate for the size.
Yeah, I can probably link put a link to a folder where you can put it in. Okay, yeah. I totally misunderstood that.
That way I can totally turn in the scrapbook.
All right. I do like the way you've been doing it, turning in just something so then I can rename the document to that. That's only between him and me, though. That's not relevant to anyone else. That aspect. Okay, so now that Leslie's here, we totally can move into where I ended last class period. This equation, I put a box around. I said, that's where I wanted to get to so we have more homework problems we can do. We had from relativity Einstein's equation that said the rest energy, E sub 0, is equal to mc squared. What did he mean when he says the rest energy?
Potential energy.
Okay, it is a kind of potential energy. A kind of. What were you saying?
Non-accelerating?
It's what?
Non-accelerating?
Well, not just non-accelerating, also not moving. So this is energy something has if it's isolated and it's not moving. In other words, it must be energy it has just because it has mass. So mass is a form of energy. And this is where things get weird because you learn, in physics textbooks and chemistry textbooks, they tell you conservation of mass is one of the rules. And I was looking at somebody's chemistry lab problem where they were using conservation of mass. But mass isn't conserved. Mass is simply a form of energy according to relativity. So if we have something change, it could change mass and release that mass as energy. So in a radioactive decay, I told you it's going to a lower energy state. Well, if it's going to a lower energy state, that means its mass is going to change. And so we talk about something we call the disintegration energy. In fact, usually we use a Q for the disintegration energy. Disintegration energy. And the disintegration energy is simply the rest energy you started with minus the rest energy you end with. So if the rest energy goes down, that means the mass goes down, then energy is going to be released. What happens if the mass goes up? Mass going down, energy is released. So what happens if the mass goes up? It has to have energy go into it. So you've learned chemistry terms. What do you call a chemical reaction when energy is released? Exothermic. So a reaction where Q, the disintegration energy, is positive, is exothermic. If that occurs, it's going to release energy. Well, if it can release energy, it's something that's likely to occur. How likely? Well, that's a different question. But something that's likely to occur. But if it's something that is needing to absorb energy, what do you call if it's going to absorb energy? Endothermic. It can't happen on its own. It has to have something make it happen. And so I'm just going to go off a little on a related tangential topic and talk about stars. We have a couple people who've taken astronomy. We have these elements in the periodic table, and where do these come from? Not counting the man-made ones. Where do they come from?
Isolating things.
They come from stars, original. I mean, your answer is interpreted differently, my question, than what I was meaning. So it's not a wrong answer, it's interpreted differently. These elements were created in stars. According to the scientific understanding of how the universe came to be, you had a huge amount of energy suddenly appear out of nowhere. Now that's one of the magics of science, right? They assume that it occurred because it had to occur for the universe to be here. But what would cause it? I believe, just throwing in my theology right here, I believe that God created the laws of physics and God put the energy in. So I do believe in a Big Bang, but I believe that God made it happen. In fact, I think I told you about Fred Hoyle. Did I tell you about Fred Hoyle? He was a person who was studying nucleosynthesis, the development of these elements, like I started this topic on. He rejected the Big Bang theory because he said, how would it all begin? It would require a God. And he was a staunch atheist. He said, I can't accept the Big Bang theory because it requires you to believe in a God. Further on in his career, okay, so basically because of that stance, he was relegated to the outskirts of science. His research won a Nobel Prize, but he personally didn't. He came up with a rather cockamamie theory about about how the universe exists and whatnot to not invoke a God. But then later he was studying the nucleosynthesis. So this energy, as we understand it, was very, very high energy density. A lot of energy per small volume. And in that form, it basically only exists as electromagnetic waves. But as things expand, you've learned laws of thermodynamics first semester. If things expand, the temperature's going to drop. And so as the universe expands, the temperatures drop until you can start having energy, electromagnetic waves, converted into mass. There's a process we call pair production, where electromagnetic waves produce mass. Now we have some problems here because our universe is predominantly what we call matter, with a very small amount of antimatter. And generally speaking, you should have the same amount of both. There was a Nobel Prize given out, about 13 years for people who came up with an explanation for this asymmetry. As things continue to expand, you produce electrons and hydrogen and protons. And you can produce higher energy variations, like you could produce muons and tauons, but they will decay down to those. So basically now you have hydrogen and electrons in the universe, and the hydrogens will collide with other hydrogens with really high speeds. Well, because of those really high speeds, they can get close enough for the nuclei to actually interact via the strong and weak nuclear forces. And you can make them stick together. Why would they stick together? Energetically, what situation would make them stick together?
If those strong, weak nuclear attractions are strong enough to where it would warp energy.
Yes. If the forces, the strong and weak nuclear forces, are creating a strong enough attraction that it's lower potential energy to have them stay together. And so you can have two hydrogens bang each other and fuse together, and then they form, actually one of those hydrogens is going to spontaneously undergo a process to disappear and be replaced by a neutron, and then you have deuterium. And then if you have another hydrogen, the deuterium can become a tritium. You have deuteriums collide, and you can make helium plus two more protons, and that's how we have helium. And so helium comprises about 8% of all of the atoms in the universe, according to Big Bang. And about 91-ish% are hydrogen. If you add those together, that's 99. What happens after helium? Well, if you have a hydrogen, a proton, hit a helium nucleus, how many things would you have in the nucleus if they stuck together? 4 for helium, 1 for hydrogen, you'd have 5. There are no stable elements with 5 things in the nucleus. And so that process can't go forward because there's no stable elements. You could, in very low probability situation, have either a deuterium or 2 protons at the same time hit the helium, and then you can make something with 6 things in the nucleus, and it can move on. So you can make things with 6, 7, but then there's again nothing with 8 things in the nucleus. And so there's another stopper. Basically, in the Big Bang, the only things that were made were up to having 8 things in the nucleus. And so we have this entire periodic table, and they're not creating the Big Bang. Where do they come from? And that's where my 2 astronomy students, stars. Stars right now, what's going on in our sun, as we best understand it? Hydrogen banging into other hydrogen. That strong nuclear force is making them stick together and release energy. If they're releasing energy, what's happening to the mass? It's decreasing. So you have these 2 protons that come together, and they produce deuterium that has less mass than 2 protons alone. And so we can use this equation to calculate how much energy is released when that occurs. And then we have hydrogen and deuterium making a tritium, 2 tritiums making the helium-4, and 2 protons. Each of those have mass. What's going to happen when our sun runs out of hydrogen? I know you 2 know. What explodes? Okay, it explodes. If our sun was big enough, that would be an ultimate reality. It's not going to because our sun's not big enough, not enough mass. With our sun, though, when it runs out of hydrogen, right now it has a big nuclear fusion bomb going off in its core. Gravity is compressing, keeping it contained. Without gravity, it would all just dissipate. And so we have a controlled nuclear fusion reactor. But when we run out of fuel, when we run out of hydrogen, well, the reactor is going to slow down. Right? It's not going to run out like that. It's going to taper off. As it tapers off, gravity is going to compress it more. As gravity compresses it more, it's going to get hotter and higher pressure until we reach the point where the helium will start fusing. That is, helium will merge with other helium. But here's something crazy. How many nucleons are in helium? 4. But what did I say about 8? Not possible. And so in order for us to have fusion, we have to have 3 heliums come together. So they call it the triple alpha process. And so our sun will fuse helium into carbon. And that, just think about it, took 4 hydrogen to make 1 helium. And so we have 1/4 as much atoms for fuel. And this process requires much higher temperature and pressure for it to go. And because of that, it's going to have a much bigger explosion as well. And so the helium is going to go up real quick. And when it runs out of helium, we have carbon. What's going to happen then? That's kind of a trick question. Nothing, because the pressure and temperatures are not high enough to make carbon fuse. And so our sun will end up with a carbon core because of this nuclear fusion process releasing energy. but not having enough energy to make carbon fuse. Now, if you had a really massive star, that really massive star would fuse carbon, form, well, actually, carbon, there's a lot of different ways things can go. But it will fuse all the way up to creating iron. So we can create all the way up to iron in supermassive stars. But when you get to iron, you suddenly have a reversal. Up to iron, when you added more nucleons, the potential energy per nucleon dropped. So it was more stable. But beyond iron, if you add more nucleons, the potential energy per nucleon rises, it's less stable. And so you can't release energy by fusing anything that's going to produce something larger than iron. So that's the end result. So at that point, your bomb in the center just stops. And then things come crashing down, and you have two things that can happen. One is you make a white dwarf, and the other one is, well, no, not a white dwarf. You make a neutron star, and the other one is you make a supernova. It's in this collapse that, well, I have to think about this. I almost said it wrong. No, you're going to make a supernova. Well, it's in the collapse that all the rest of them are created. It's exothermic, so when you create something like gold, it's going to cool the reaction down because it took energy in and doesn't release anything. And so those endothermic, those endothermic ones cool the reaction when you're in that big explosion. So all of that, yes, that's a little off topic for the textbook, but totally on topic for the topic. So energy released is mass of parent minus mass of daughter. Now I'm going to have you guys do a calculation with this in one more slide. So get ready. Here's the masses of a proton, a neutron, and an electron in kilograms. Atomic units. We usually use atomic mass units for this calculation, or in MeV per c squared, which is very useful. This conversion factor, a lot of people don't even realize that the atomic mass unit is based on Avogadro's number. The atomic mass unit is defined as 1 gram divided by Avogadro's number. And so we can take that mass and we can convert it into MeV per c squared, which makes life real easy for us. So that number, 931.4941, I probably don't need all 7 digits there. That's a conversion factor that makes it easy to use E equals mc squared. Your c squareds will cancel. By the way, on that problem 16 on the test where I had the wrong answer there, that was one that most people actually did a really good job on. I just added 10 points to everybody's test score in anticipation that the time they spent trying to find an answer to match my wrong answer would have caused lower points elsewhere. So that's what I did with that question. I think that meets with everyone's approval, doesn't it? I mean, I was listening to your comments and tried to go with the one that I thought worked best there. But the problem that most people made, if they had a problem, was that they didn't cancel their C's. You have gamma is equal to 1 over square root of 1 minus v squared over c squared. For v, they'd put like 0.75 c, and then they'd put 0.75 multiplied by c, square it, and then just cross out the c squared below instead of canceling the c's. And so they ended up with gammas that were very close to 1. Okay, so moving on. This number is going to be very important. You calculate the energy release with that equation. So let's do an example problem. By the way, here is a link to our textbooks where you get the masses for the different isotopes. I wrote them down for you on this next slide. So back to this figure that we've already seen. Can't raise it too much because I did the work down below. The uranium decay example equation. How much energy is released in one fission event here? How do I know it's fission? Because it's breaking uranium into smaller pieces. So, paper. I actually zoomed it in to try to make my handwriting a little neater.
I actually really miss astronomy class. That was fun.
By the way, when you do these calculations, keep all the decimal places. With this one here, it turns out that you're actually going to be measuring it in 0.1 something atomic mass units, but oftentimes it's not nearly such a big number, so you need to keep them all. And guess what you're going to be doing on the homework for Wednesday? A lot of things that look like this. Yes, sir. Okay. Because I gave you the mass for uranium-235, use that one. Most sources don't show you the uranium-236 because it's unstable and splits. Yes, the equation is parent, which is the beginning of things, minus daughter, which is the end of things.
So when you say so is this even talking about the current or just okay, so when you say daughter, do you have to subtract it by those two items?
I'll put boxes around them to make sure it's clear. The parent is what you start with, the daughter is what you end up with.
So with the daughter, how do we get the just one number for those daughters, I guess?
Okay, so you have barium-141, so that's this. You have krypton-92, that's this.
So do we-
You have 3 neutrons, that's these.
Okay, so but are we like
You combine them.
add them? Okay.
I was wrong. What did you get?
Okay. Okay, mine is a little clearer.
That's why I was like,
Yeah. What did you get?
Thanks. You.
Yeah, what did you get? Well, okay, I didn't get that.
Oh, mine is an international.
Wait, do we have to convert them?
That's why I asked you.
Is that what you want?
If you use those numbers, it's going to be on.
Yeah, well, you have to change some of the mobile, so, yeah.
That's probably why mine is different.
Oh, sorry.
It's unconventional. Oh, but it may be right. So it's, yeah. Yes.
You know, I want to get different. I feel like I might be wrong.
Because this is u times c squared. Well, no, that is.
This would be super hilarious if you need to understand the computer. Like, I look at his doors and it looks like the shadows under it.
This, you have this times.
This is literally the clearest it is.
We had a conversation about this.
With what, the screen?
Yeah.
Yes.
Yeah.
Like, it's literally the clearest the screen has ever been.
My eyes.
Leslie, it's not the screen, it's your eyes.
I know it's my eyes. I never said it was the screen. Jeez.
Alright, did you get 1.108?
Oh, I appreciate it.
Okay, how do you guys count?
I don't know if it's right or which
Did our best.
I haven't answered your tools
And that's
And that's just
I have both. I'm pretty freaking sure I'm wrong.
Oh, is it supposed to be?
Because it's supposed to
It's
be
just
the parent
NVDs.
minus the other.
It's a lot easier if you just get rid of these.
Is it
That's
but
what
then
I
we
did.
added it.
Yeah, well,
Because the units
no, I'll
already-
go over it here.
Because I still times it
Okay,
by
so let's
speed.
see.
Let's
That's
do
right.
We could be.
We're supposed to times it by speed.
All right, how do you guys do that?
Are we supposed to times it by speed of light squared?
It depends on what units you use.
Yes, you have to multiply by the speed of light squared, but if you use that 931.4941 MeV per c squared,
I
you have
already
the c
have
squared. Okay, I'm going to go on to the solution. Mostly because we only have 5 to 10 minutes left before we do the course evaluation. So our equation was the energy released is mass of the parent minus mass of the daughter times c squared. So I put in individually the mass of each thing. So this was the uranium-235. This was a neutron. This was the barium, whoops. Yeah, it's barium. 141. This was the krypton 92. And this was 3 neutrons. And so here's the numbers you get when you add up the parents. So this here is the mass of the parent combined. This is the mass of the daughters. If you subtract them, it's 0.186. And in this case, I have 6 significant digits, so I kept 7. Multiplied it then by c squared. Notice there's a c squared here. This here is a conversion factor. I should have put MeV per U c squared because one atomic mass unit was equal to 931 point whatever MeV per c squared. And now my c squareds are going to cancel, which, as I said, is a thing that often got messed up. My U's cancel, and I'm left with 173.289 MeV. On the atomic scale, that's a fairly large amount of energy released. And remember, if you have a fission bomb, you're going to have 3 neutrons that come out of this that can go on to cause another reaction. So the rate of reaction is going to increase exponentially. Now, what if you want to make a fission power plant instead of a fission bomb? What's the difference in a bomb and a power plant? One is more beneficial, and I think we'll all agree that it's the power plant.
Isn't one fission and one fusion?
Well, you have fission bombs and fusion bombs. We only have fission power plants right now. But the key with the fission power plant is you don't want it to have an exponentially growing reaction. Because if the reaction is exponentially growing, it is a bomb. Right? You can make that fission power plant into a bomb real easy. So what they have to have in fission power plants is they start by having a fuel rod. What is that fuel rod? Well, there's different variations. The one that I talk about for this class is uranium-235. Now, if you have too much uranium-235, you have something special happen. These neutrons that come off of this reaction, these are hot neutrons. Just define the difference in thermal and hot or fast. What's the difference in thermal and these? Thermal is the slower ones. And in order to have a good chance of a reaction, the neutrons have to slow down. So if I just have a few uranium-235 atoms, neutron comes off, it may bounce around a little, but it's not going to be absorbed because it'll be going too fast. And the neutrons are lost and there's no bomb. But if I have enough uranium-235, the neutrons will bounce around and slow down with each bounce until they slow down enough that they get absorbed. So if I have enough uranium-235, my neutrons will slow down enough to cause another reaction, and then suddenly it's a bomb. So depending on how much stuff you have, uranium could be a bomb or not a bomb. That's where we have the term critical mass. Critical mass is if I have a clump of pure uranium and it has this much mass, the neutrons on average are going to bounce around enough and slow down enough that they're going to cause another reaction and it's a bomb. If it's less than that, on average, they're not going to slow down enough and they're going to be lost and it's not a bomb. For a power plant, you want it to be right at that level. So they have these rods, and each rod is subcritical. Each rod is itself not a bomb. Good plan, right? But then they put the rods together, and so neutrons that leave one rod could go into another rod. And then they put something in between the rods. Something in between the rods to slow down the neutrons. If you slow them down, the neutron leaves this rod and hits this rod. What's going to happen? It hits the second rod. Comes out of this one fast, it comes into this one thermal. What's going to happen? You know what? It's going to be absorbed and cause another fission reaction. And so now we use water as a moderator, something that moderates or slows down the speed of the neutrons. And so now we have something that can blow up, right? Well, that's no good. So we put fuel rods in, then we put the water in the moderator, and then we put something else in there that's going to absorb neutrons to take them out of the equation. And so that's called a control rod. And the control rods are raised or lowered to keep the reaction rate constant. So that on average, one neutron from each reaction goes on to cause another reaction. So that's how they control a nuclear reactor to keep it from blowing up with those control rods. If they see that it's heating up, that means you have more than one neutron going on to cause another reaction. They lower the control rods a little more, and you absorb more neutrons, and it slows the reaction down, cools it off. So the nuclear reactor, you can see there's things that can go wrong. And there's design things that can be silly. Like I talked about lowering the control rods. Why would you want to lower them? Because in case of catastrophe, you would like to drop them and let gravity do the job for you, getting them in place. You don't want to have machinery that has to push them around. You want gravity to do the job. That's all I'm going to talk about for reactor design here, because we're really low on time. This here goes into what I talked about with stars. This here is the binding energy per nucleon. That's how strongly the nucleons are held together in a nucleus. And so these are actually calculated based on the masses of all of the different isotopes, well, representative isotopes. And what you see is the peak of this chart is iron. So iron is the thing that if you're doing fission, you're going from a higher mass breaking into lower mass pieces. If you're doing fusion, you're going from smaller pieces to higher mass pieces. And the amount of energy released per mass is proportional to the difference in the heights of your starting and ending points. So let's take, for instance, fusing hydrogen into helium. Hydrogen, you have a single proton. Its binding energy per nucleon is 0 because it's not bound to anything. It's alone. So hydrogen 1 is right here. It's not shown because, well, how do you show something that doesn't exist? Helium 4 is up here. That's a difference of about 7 atomic mass units. 7 atomic mass units? No, excuse me. 7 MeV. Wow, that was wrong. 7 mega electron volts per nucleon. So per mass unit. That's a huge amount of energy released compared to, let's say, uranium. So you go from uranium to, let's say we went to krypton and even forget the barium. We go from about 8 to 9, a difference of 1 MeV per nucleon. Now, sure, uranium has 235 nucleons, so the fission of one uranium atom will release more energy than the fusion of 4 protons. But if you have 235 protons, so you have the same mass, you get much more energy released than if you had 1 uranium atom. So fusion has a much bigger potential for producing energy per mass. And some might say, well, why don't we try to make a nuclear reactor to fuse hydrogen into iron? Well, the conditions for that are incredibly hard to do. You have to have a supermassive star to reach the temperatures and pressures necessary to do that, and it's only during the collapse of the star. So, yeah, that's not feasible. That's why fusion, better energy source. Also, waste products. We talked about what do you do with that waste from nuclear fusion or fission? Well, you've got this radioactive stuff that you have to do something with. Something like dig a hole and bury it. Whereas with fusion, you're producing actually, generally speaking, non-radioactive things. There is some radioactive stuff that you produce, but generally it's non-radioactive stuff, so you don't have a waste problem. Similarly, with a fission bomb, you're going to have radioactive waste spread out everywhere. With the fusion bomb, lots of neutrons go flying by, lots of energy, and then no residual radiation, well, not much. So there's, after a fusion bomb, you can come march in with your soldiers a few days later, maybe. Fission bomb, no. Okay, I'm skipping over that question. I don't have time to talk about radiometric dating because we do need to do course evaluations. So I'm stopping the recording now.